Today we're going to start talking about sequences. So just getting mostly the vocab down and what a sequence is. So I want you guys to take, probably take about 5 minutes. Do the do now, do number 1 and number 2. Pause the video and play it once you're done. So if taking a look at this sequence, what are going to be the next 4 terms? In order to find the next 4 terms, we should probably look at the pattern first. So between 4 and 7, and then 7 and 10, we're adding 3 every single time. So we're adding 3 to the previous term. So if I keep on adding 3, the next term would be 22. Add 3 to 22, 25, 28, and 31. And what is the pattern to the sequence? Well, we're adding 3. So adding 3. And we're adding 3 to what? This is important because we're going to be talking about the previous term a lot for sequences. So we're adding 3 to the previous number or term. And we're adding 3 to the previous number to obtain the next number. That's just a basic sequence right there. And number 2, at Mount Morris Elementary School, the auditorium has 35 rows of seats. The front row has 12 seats, and each subsequent row has 2 more seats than the previous row. How many seats are in the 14th row? So there's lots of ways of doing this. What I'm going to do is I'm just going to put all the rows we have here. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is a way you can do that. There's a lot of ways you can do this. So the first row has 12. And then each subsequent row has 2 more seats. So we're just going to keep on adding 2 seats until we get to our 14th row, which is what the question's asking us for. For 36. And the 14th row has 38 seats. So that would be 38 seats. So that's a little introduction to sequences. What should I be able to do by the end of the day? I can define a sequence. I can create a sequence of my own. I can write a recursive formula given a context. I can interpret a recursive formula and state any term in the sequence. I can graph a sequence. I can define an arithmetic sequence. And I can decipher whether a sequence is arithmetic or not arithmetic and provide reasoning. So let's go to the next page. So a sequence is an ordered list of numbers that often has a pattern. The first term is denoted A1. So remember, when it's a subscript, that denotes the location. Second term is A2. Third term is A3, because this would be the third term. And you can write it as, so just A1, A2, A3, A4, A5, A6, A7, and it keeps on going on forever. Other common notations. This is important because you're gonna want to make sure you realize this is still a sequence when they're using this notation. You could use A1. You can use F1. Those are very common notations, and there's other notations also, but these are the most common. So then the second term would be A2, or if you're using the function notation with F, it would be F2. So I would make sure you start this because I know this is where some students get tripped up because we're so used to seeing sequences like this that when you see it in a different notation, it might trip you up a little bit. So make sure you are good with that notation also. So here's another example. What is the pattern of this sequence above? Well, before I look for the pattern, let's just talk about the terms. So the very first term is A1. So this would be A1 would be 3. Then A2 is 9, A3 is 15, A4, A5, A6, A7, and it keeps on going on. You could also label it as F1, F2, F of 3, F of 4, F of 5, F of 6, F of 7, and so on. You could also do A1, A2, but I'm not going to write that down. So what is the pattern of the sequence above? Well, it looks like we are, check with every single one, but yeah, we're adding 6 to the previous term. So we add 6 to the previous term. And what is A5? Well, A5 is right there, the 5th term, which is 27. A of 1 is the 1st term, which is 3. And F of 10, well, we don't have that yet, so we got to keep going. We have to go to add 6 to get the 8th term. Then from the 8th term, add another 6 to get the 9th term. And add another 6 to the 9th term to get the 10th term, which would be 57. So that's all sequence. That's sequence vocab, sequence notation. Make sure you're able to define a sequence. And I just want you guys to pause the video and create a sequence of your own. So state the first step, which is state the first term. Second step, state the pattern of your sequence. And third step, state the first 5 terms of your sequence. And play it once you're done. So I'm going to create a sequence. I'm just going to say, we'll say the first term is, and you can really do anything here. I'm going to say the first term is 5. Keep it a simple sequence. And state the pattern of your sequence. I'm going to add 10 to the previous term. You guys could multiply. You guys could divide. You guys could subtract. I'm just adding for this one. So first 5 terms. My first term will be 5. Add 10, 15. Add 10, 25. Add 10, 35. And add the last 10 to get 45. So those would be the first 5 terms of my sequence. Again, I don't think anyone's got the same exact sequence as I have. So on the next page, using the sequence I just created, I guess you could use your sequence too if you want to, but the sequence I created started with the first term of 5 and then added 10 to the next term, from the previous term to get to the next term. Let's list as many terms that will fit on the page. I'm going to give you guys 2 minutes. Pause the video. List every single possible term you can list, because we want to list the entire sequence. Five, 15, 25, 35, 45, 55, 65, 75, 85, 105, 115, 125, 135, 145, 155, 165, and we can keep going on forever and ever and ever and ever. So listing a sequence out by all of its terms is really not as beneficial or as efficient, because it can keep going on and on forever. So that's when we introduce a formula. So we can represent the sequence as a formula and don't have to list out every single term. So this sequence would obviously go on forever. There's a better way to represent it, and one formula we can use is called the recursive formula. So the recursive formula is a way of writing sequences that relates each term of the sequence to the previous term. That's why we've been using previous term a lot. You must always state the first term to specify where a sequence starts. Because if you told me, oh yeah, my sequence is just adding 5 each time. Okay, like what? So I'm adding 5 each time, but to what? You're not specifying what it is. So you want to say, oh, it starts at 7. And then I'm adding 5 each time, because then I can actually find the numbers. If you don't tell me where to start, I have no idea what to add that 5 to. So we have to always state the first term and then state the rule that's happening. So let's look at how I would write my sequence in a recursive formula. So notice we state the first term. You always have to make sure you state the first term. And then this is the rule that's happening. So here's the rule. It says AN. So AN is, you can think about that as the term we are looking for, or the term we are, the current term or term we are finding. And then you take A of n minus 1, which is the previous term, and we add 10. So that's really big. I want to make sure you guys understand that A of n is the term we are looking for in this instance, and then A of n minus 1 is always the previous term. That's a very important notation. So let's put this recursive formula into words. Well, the first thing that's happening is the first term is 5, so the first term is 5. And then what's happening? Well, to find any term, what you must do, to find any term, what you must do is take the previous term which is an minus 1, and add 10. And how can I put this in different notation? Well, we could use the A1 in function notation. So we could say A1 is equal to 5, and then AN is equal to AN minus 1 plus 10. So we could use that notation, or we could also say the function notation. So the first term with f. So the first term is 5, and then f of n is equal to the previous term. So it'll be f of n minus 1 plus 10. So that's two other ways you will see this written. I want to make sure everyone's good with using all three kinds of notation, because you're going to see them all. Let's go to the next page. So on the next page, we are just going to interpret each of the three recursive formulas and find the first 5 terms in each sequence. So we'll do number 1 together. Actually, wait, no, let's not. Pause the video. I want you to try your best to interpret number 1 and list the first 5 terms, and then play it once you're done. So number 1's telling us the very first thing is the first term is 3. So I'm going to say the first term is 3. Is 3. And then what's happening that? Well, to find the next term, so I'm going to say to find the, you can say the next term, or it's an, so I'm going to say to find the nth term, because we don't know what it is. So say it was A5, it'd be the 5th term, but it's n, so we say the nth term. Take the previous term, which is A sub n minus 1. And what we're doing, we're subtracting 2. And subtract 2. So the first term would be 3. Subtract 2 to get 1. Negative 1. Negative 3. And negative 5 would be the first 5 terms. Let's look at number 2. Number 2, again, I want you guys to pause the video, interpret this sequence, and list the first 5 terms, and play it once you're done. So, very similar to the first one with the first term. The first term here is negative 4. So we'd say the first term is negative 4. And then how are we finding the next term, or how are we finding the nth term? Well, to find the nth term, this one's a little bit different. We're not adding or subtracting to the previous term. What we're doing is we're multiplying by 2. So we're taking the previous term and multiplying by 2. So to find the nth term, take the previous term. Or you can just say, actually, I'm not even going to say take the previous term. I'm just going to say to find the nth term, multiply the previous term by 2. List the first 5 terms. Well, the first term is negative 4. Times that by 2, you get negative 8. Times that by 2, you get negative 16. And keep multiplying by 2 until you get to the 5th term, which should be negative 64. Now, the third one's going to be a couple of different operations. We're not just going to be multiplying or just subtracting. So, for the third sequence, I want you guys to do the same thing, interpret it, and then list the first 5 terms. Pause the video and play it once you're done. So, similar beginning. The first term, oh wait, look, it's in different notation. Doesn't matter, all means the same thing. So the first term is 1. And then we're always trying to find the next term or the nth term. So to find the nth term, what's happening here? Okay, so we have the previous term right here, a of n minus 1. And think PEMDAS, what do we have? What's happening to this term, the previous term first? Well, we're multiplying by negative 3, and then we're subtracting by 2. So to find the nth term, we're taking the previous term, which is a of n minus 1, so, and multiplying by negative 3 first. So multiply the previous term by negative 3, then we subtract 2. So let's list the first 5 terms. And this one, when they get a little bit more steps, I like to show work here so I don't make a simple mistake. So the first term, that one's easy. They gave that to us. That's 1. So to find the second term, a2, what we need to do is we take negative 3, we multiply negative 3 by our previous term, which in this case our previous term is 1. So we do negative 3 times 1, then minus 2. We should get negative 3 minus 2, which is negative 5. Do the same thing for the next step. The a of 3, so the third term would be, we use the same equation, negative 3, but now we have to do times the previous term. And our previous term is negative 5, because if we're the third term, our previous term is the second term. So we plug in our second term, which is negative 5. Continue with our equation, minus 2. You would get 15, because negative 3 times negative 5 is positive 15, minus 2, which is 13. Okay, we gotta find our first 5 terms. So now we have to find the fourth term. So a of 4 is equal to negative 3 multiplied by our previous term, which is 13, because that's the third term, and we're on the fourth term. And subtract 2, we're getting negative 39 minus 2, which is negative 41. And our last term is the fifth term, since we just are listing out 5 terms. And we still use this equation. Where's that negative 3 and minus 2 coming from? It's still just coming from that rule, because we have to keep on following that rule to find the next terms. So that would be negative 3 times our previous term, which in this case is a of 4, because we're on a of 5. So the previous term would be a of 4. So we plug in that negative 41 minus 2. Negative 3 times negative 41. Feel free to put that in the calculator. That's 123 minus 2. So that would be 121. So the first 5 terms would be 1, negative 5, 13, negative 41, and 121. Let's go to the next page. On the next page, Simon is saving up for a new pair of soccer cleats. He has $15 saved from his first week and then saves $10 each week from mowing lawns. Write a recursive formula to represent how much money Simon has saved in n weeks. So we know we're using sequences here because it says write a recursive formula. So recursive formula, that should be a little tip. We are using sequences. So think back to the recursive formula. We want to first state, no matter what, first always state what the first term is. So what would my first term be? Well, take a look at this. It says Simon has $15 saved from his first week. So our first term, I'm going to write it as a sub 1 is equal to 15. And then our rule, recursive formula, we always relate to the previous term. So the nth term is equal to something's happening with the previous term, a at n minus 1. And let's take a look. It says he then saves $10 each week from mowing lawns. So he's increasing $10. That would be a plus 10. So we're taking the previous week or the previous term and adding $10 each week. So if we fill out the following table, the first term is 15. And then we just keep on adding 10 each week. So this would be 25, 35, 45, and 55. So let's graph this sequence below. Well, our y values or our terms are going up to at least 50, or going up to 55. So we're going to want to make this graph go up to 55. In order to do that, if we count by 5s, we're going to not barely have enough. So I'm going to count by 10s each time. So 20, 40, 60, 80, 100. If you count it by 5s, we're only going to get to 50, and we got to get to 5 more than that. And then I'm going to count each box in the X by just 0.5, just so I space it out a little better. You don't have to do this. You can count every one by 4. It's just going to be a little more scrunched if you do. And let's plot our points. So 1, 15. This would really be 1, 15. You can write out the points if you want to. 2, 25, 3, 35, 4, 45, and 5, 55. So 115 would be here, 225, 335, 445, and 555. Let's make those dots just a little bit bigger so they're easier to see. So I want to show you guys the number one mistake that happens after this. You do not want to do this. Okay, let's just draw the line because it's a linear equation and put arrows on the end. What is wrong with this? Well, there's a couple things. A, we are talking about weeks in the x-axis. So if we go into the negative weeks, that's not a thing. We can't go back in time yet. So we can't go back in time. We don't want to include the negative portions of the x because we're not going back in time. There's another thing incorrect about this. We're saying in between each value, there's like a term, like right here would be a of 1.5. That is not the case. There is no 1.5th term in a sequence. There's only the first term, the second term, third term, fourth term, only whole numbers. So that is why we never connect the dots for a sequence. There's only the first term, then the second term, then the third term, fourth term, and fifth term, sixth term. There is no like 6.5th term or the 6.3rd term. So they're only coordinate points. There's only dots. So you don't connect the dots for any sequence, really. So, what quadrants should not be included on our graph? And explain your reasoning. I want you guys to actually do these next two questions. So pause the video and answer these next two questions. And play it once you're done. So what quadrants are not included? Well, this is quadrant 1, 2, 3, and 4. So which ones aren't included? Well, 2, 3, and 4. And why are they not included? Well, you could just say, well, all the terms are positive, so they're going to be in the first quadrant. Or you can relate it back to the context, which I think is a little bit better of an answer. It's because you can't have negative time, and in this scenario, you can't have negative money because Simon's making money. He's not losing money. So I'd say because you cannot have negative time. And sometimes you will have negative money if you're losing money, but Simon's only making money right now. So I say, and in this scenario, you cannot have negative money as Simon is only making money. And how does the graph of a sequence differ from graphs of other equations? Well, think about other equations. If you plot a bunch of points, you would have a nice curve or a nice straight line. In this instance, so for sequences, you don't connect those points. So you do not connect the points. And why is that the case? Well, think about that for a second. It's because there is not a decimal there's not a decimal term. Like there's not a 2.5th term of a sequence. There's only the first, second, it's only whole numbers, third, fourth. At sequence, you could also say sequence only has term numbers that are whole numbers. Only has term numbers that are whole numbers. Think like A of 1, A of 2, A of 3, and we can keep on going. Those term numbers are all whole numbers. On the next page, we have a checkpoint here. I just want you guys to do 1, 2, and AB, and then 2 has A, B, and C. And pause the video. This should take some time, so take your time. This should honestly take like 5 to 10 minutes. And pause the video and play it once you're done, and I'll show you the answers. So the first term is a half, and to find the nth term, you're taking the previous term, multiplying by 4, gotta follow PEMDAS, then subtracting 2. There's the first 5 terms. Make sure you show some work for this, because it's so easy to make a mistake. If you don't show the work, you're gonna make a mistake. Please don't test me on that, because trust me, you will at least down the road once. So show the work, especially when it gets a little bit more difficult. I mean, when we're adding just 2 or subtracting 2, or even just like multiplying by 4, and that's it, you know, you can get away with not showing work, but when you have to do multiple different operations, please just take the time and show the work. Number 2, it's a little bit different than we've seen, but I think you guys are able to do this one. So the first thing is the first term is 2. That's not changing. So the first term is 2. And then look what's happening to find the nth term. So your wording might be a little off on this, which is completely fine. It's the first time you're kind of seeing one like this. So to find the nth term, you're taking the previous term, nothing new there. But in this case, what are we adding? We're adding n, which is the term number. So, for example, if we have the third term, what we're doing is we are adding the previous term, so that would be the second term, and then we're adding not any term, not adding the third term or second term to it, we're adding the term number, which is n in this case. So n, this is the third term, 3 is the term number, so it would be a of 2, the second term, plus 3. So that's what's written here. So to find the nth term, you take the previous term, which is a of n minus 1, and you're adding the term number. So not the actual term, but the ordered number. So if it's the third in order, you would add 3 there. And here's what the work would look like for that. So the first term is 2, and then notice to find a of 2, well, the previous term was 2, so you take the previous term and add it to the term number, which in this case is 2, again. And then similarly, for a of 3, you take a of 2, which is the previous term, which was 4, and then you're adding the term number. It's the third term. I'm going to do this for every single one, because I know some people out there that are confused by this a little bit. So the next one, the a of 4, you find the previous term, a of 3, which is 7. And then you're going to add the term number. It's the fourth term. So you add 4. And similarly, for a of 5, you take the previous term, which is 11, and you add the term number. We're on the 5th term. So we add 5. And when you do that, you get the 5th term to be 16. And when you graph this, make sure you don't draw that line through them. You'll see this is not linear. It doesn't have a constant rate of change. So it should look something like that. Let's go to the next page. So on the next page, so we've been talking about sequences. Sometimes we're multiplying. Sometimes we're adding and subtracting. Sometimes you can even divide. Sometimes we are multiplying and adding or subtracting. But there's a special kind of sequence that is just either adding or just subtracting, and that's what we call an arithmetic sequence. So an arithmetic sequence is a sequence that has a common difference between terms. So the common difference, it could be negative or it could be positive. So in this case, this is a similar one, we're adding 6 each time. So our common difference here would be 6. So in a common difference, we use D for common difference is equal to 6. And then let's check out the next one. Our common difference here is we subtract 4. Subtract 4, subtract 4. Is it all the way out throughout? Yes, it is. So we're subtracting 4 each time. So the common difference here is negative 4. Or I should say minus 4, either way. I'll show you guys one that's not an arithmetic sequence. So how about, I don't know, we'll do 2, 4, 8, 16, 32. We'll keep going like that. So this one has a common difference. We add 2, we add 4. Actually, it doesn't have a common difference because we're adding a different amount each time. So there's no common difference. This is not an arithmetic sequence. But the other two are arithmetic sequences because we're either adding 6 the whole time or subtracting 4 the whole time. So the general form for any arithmetic sequence is very similar. Actually, we've been doing arithmetic sequences, you just didn't know it. It's just the first A1 equals the first term, nothing new there. And then the nth term, or the term we're looking for, is the previous term plus whatever the common difference is. So if I were to write the recursive formula for our two examples here, we'll say this is example 1 and we'll say this is example 2. Well, for example 1, we have first state our first term. So our first term is 3, so I'd say A1 is 3. And then let's state our rule. So a of n, the nth term, is equal to the previous term, a of n minus 1, plus our common difference. And our common difference for the first one is 6, so we plus 6. And how about number 2? Well, our first term here is 4. And then what's our common difference? We're subtracting 4 each time. So our rule would be the nth term is equal to the previous term minus 4 in this case, because we're subtracting 4. So I want you guys we'll do number 1 together, and then I'll have you guys do the rest. So determine whether each of the following sequences is arithmetic. Think arithmetic. What does that mean? Common difference. It has to have a common difference. Explain your reasoning if you think it's arithmetic or not. And then find the sequence's recursive formula. So looking at number 1. Is this arithmetic? Let's see. Does it have a common difference? We add 7, add 7, add 7, add 7. Yeah, that is recursive. Excuse me, that is arithmetic. So it is arithmetic. And why is it arithmetic? Well, it's because the sequence has a... And what's the big words there? Common difference. And the recursive formula for this one would be a of 1 is equal, so the first term is equal to negative 1. And then what's happening to the previous term each time to find the next term? We are just adding 7. So I want you guys to pause the video, try 2 and 3. 2's recursive formula is something different than we're used to seeing, but give it a shot. Pause the video and play it once you're done. So let's look at number 2. Number 2, we're adding 2, adding 4. Stop right there. We already see there's no common difference because we're not adding or subtracting the same amount. So this is not arithmetic because it does not have a common difference. And this actually does not have this wouldn't have a recursive formula, but how you could write this is you could say a of 1 is equal to 2. Well, that's nothing new there. The first term is 2. And then did anyone see the pattern in this? It's actually to find the next term, you're just taking 2 and you're raising it to the term number. So let me erase the top here. This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, and we keep going on like that. So that one was a little tough. That's not one we've we'll go over more stuff like that tomorrow. And number 3, does this have a common difference? Subtract 8. Subtract 8, subtract. It does have a common difference, so this is arithmetic. Because it does have a common difference. And our recursive formula for this is a of 1. The first term is equal to 10. And then we're just taking the nth term, and to find the nth term, we take the previous term and subtract 8 each time. So that's it for the notes today. Here's the success criteria, and then the homework is just to finish the classwork.